you could have a differential equation that has more than one solution. And what we'll want to use is a linearity property, which says that the general solution is a sum of those, is all possible linear combinations of those two solutions. But we can fool ourselves if the two solutions we chose actually depended on each other. So we have to be careful to make sure we choose linearly independent functions and then take the span of all possible, the span of those functions, take every possible linear combination to form our general solution. So just like with pivots and bases, with bases we needed a pivot in every column and pivot in every row. We needed enough vectors of the right kind, linearly independent. We need enough of them to fill the space. So in this case, the space that we're filling depends upon the differential equation, the order of the differential equation. So first order differential equation, the space is one-dimensional. We're looking for just one solution that we're multiplying by a constant. Second derivative, we're looking for two separate linearly independent solutions that we then scale and span together. So one thing to help us test linear independence is something called the Wronskian. Function that tests linear independence. Now, the Wronskian actually comes up in a form that's very similar to something we've done before. It uses a determinant, but a special determinant based upon the function. So let's look at it a little bit more in depth. Recall that AX equals B for an n by n matrix has a unique solution if the determinant of A is not equal to 0. Now, this was part of Cramer's rule. Cramer's rule says that if the determinant is not equal to 0, then it is a unique solution and it exists by taking the ratio of the determinants. Okay. Now, we'll get to that later. Don't worry about that. We'll get to Cramer's rule again. But this idea we want to carry over to functions. We define the Wronskian of two functions, x1 of t and x2 of t. I'm writing of t just to remind ourselves that these are not vectors. They're actually they're not components of vectors. They're actually functions. They're not vectors here. And so I'm going to take derivatives of them. First, we have the functions themselves, x1 and x2. Then we have their derivatives, x1 prime, x2 prime. And then we take the determinant of that 2 by 2 matrix. And that is the Wronskian of two functions. How do we get that? Well, what we're going to do is fill in the first row with the functions and then take a derivative to fill out a square matrix. Now what about 3 by 3? x1, x2, x3, pretty straightforward. We get one function, two functions, three functions. And then we take one derivative of each, second derivative of each, and that fills out another square matrix. Now, what are we trying to see? We're looking for dependencies in the function, and we're searching not just at the function level, but searching down as far as we can go in the derivatives of that function to fill out a square system. Notice that if we have two conditions, two variables, then we can solve that system. It's 2 by 2, it's determined. And if we have 3 variables, we need 3 conditions. So what this first condition tells us is that the functions are not multiples of each other. They're not dependent. One is not a dependency on the other. And then the second condition says that the derivative is not a multiple of each other. The derivative is not the same multiple as the function in that sense. And then for the third derivative, we're looking at, is this third function and its derivative and second derivative, is that a linear combination of these 2 functions and their first and second derivatives? Just like we took v3 and we said, is it a combination of v1 and v2? Well, if the determinant is not equal to 0, we know they're independent. Now the tricky thing here is that functions which look like they are completely different functions, they're not the same function, but they can have a dependency at certain points. And the Wronskian finds those points. And those are the same kind of points that we have to exclude. We call them singular points, that we have to exclude from the solution, just like our existence and uniqueness theorem 3.2. That was a way to look at the discontinuities in the coefficient functions. The Wronskian is another way to check, to see what values of t should be outside the solution interval, because that is a point where you have dependency of your functions. Okay, so let's do let's look at a little bit of theory and an example with the Wronskian. So first piece, I'll erase that too. I'll write that up again. x1, x2, x1 prime, x2. There we go. Okay. If the Wronskian of a set of functions is not equal to 0 for all t in the solution interval, which is what we talked about last time, restricting the solution interval to a point where we can solve it for a unique solution. Then x1, x2 as functions, x1 of t, x2 of t, xn of t are linearly independent functions. Furthermore, if x1 of t, x2 of t through xn of t are all homogeneous solutions, that's where xh homogeneous solutions, axh equals 0. And the Wronskian of x1, x2, xn is not equal to 0 for all t in solution interval. Then these functions form an nth dimensional fundamental set of solutions to the differential equation. Now, this fundamental set of solutions is the new vocabulary that we use for the functions themselves. But really what that fundamental set of solutions refers to is the null space. If you can show that you have a bunch of functions which are homogeneous solutions, in a sense, when you plug them into the left-hand side, you get 0, whatever this A combination is. Here, A would be 1, P of t, Q of t, multiplying by the 3 components, gives you 0. If the Wronskian of all of them is not equal to 0 for all t in the solution, then they are a basis for the null space, and we call them a fundamental set of solutions. They are the basis for the null space. And we write x of h as the span of x1, x2, xn, and that span really means c1 x1 of t plus c2 x2 of t plus cn xn of t. So at the end of the day, we write our solution in terms of a linear combination of homogeneous functions that give us 0, but are also linearly independent. And we check that linear independence through a determinant. And in this case, we do it through the Wronskian. Later on, we'll see that we end up using Cramer's rule in another way to test, to make sure that they're independent, or that it only works if they're independent. Okay, so that's the last bit of theory. Let's do some examples to dig in a little bit into this idea. So again, we're going to find a two-dimensional problem, second order problem, two-dimensional, second order. We're going to find two solutions to it, check to see that the Wronskian is not 0, and then write down our solution space, our x of h, homogeneous solution, as the span of all combinations of those two pieces, c1 x1 plus c2 x2.